So we can flow through this just like the previous example on solving for a determinant. This one's a pretty simple 2 by 2. Again, we solve for the following sets of equations for the unknown currents. Again, you can see it's already set up for you. All your current 1s are in the first column, current 2s are in the second column, and your constants, which relate to your voltages, in the B, or the final column. So we extract the coefficients. Given that the coefficients are in ohms and the constants are in volts, evaluate the characteristic determinant as follows. So you'll recall we extract those coefficients, 2, -5, 6, and 10, just as we see here. And we do this times this, so 2 times 10 minus 6 times 5. Okay, this times this minus this times this. And we end up with a characteristic determinant of 50. So that'll be the denominator in our final solutions. So now we solve for current I1. Remember that we take the first column out, the 2 and the 6, and we replace it with the 10 and the 20. So 10 and 20. The -5 and 10 stays, so this times this minus this times this. So 10 times 10 minus 20 times -5 gives us then a value of 200. We divide it by 50, and that gives us our current then of 4 amps. So on the next step then, we remove column 2 and replace it with the coefficients, the voltages. So 2 times 20 minus 6 times 10 gives us 40 minus 60, or 20. So minus 20 divided by 50, which gives us a negative 4/10 of an amp. So in a circuit problem, a result with a negative sign indicates that the direction of the actual current is opposite to the assigned direction. Note that the multiplication can be expressed either by the multiplication sign, such as 2 times 10, or by using the parentheses, and we can see that that's the way they set these up in the problems. So those were our solutions. So now to take it to the next step. The next step is using a third-order determinant. Third-order determinants can be evaluated by the expansion method. We'll illustrate this method by finding the unknown current values in the following 3 equations. So you can see we've got them set up in standard form. Column 1 is all I1, column 2 is all I2, column 3 is all current 3, and then our voltage values. So now when we place these in the array, in the matrix, then this is A11, this is A12, this is A13. So A11, A12, A13, and so on until we take every one of our coefficients and place it into the metric. Okay, so the characteristic determinant for the matrix of coefficients for this set of equations is formed in a similar way to that used earlier for the second order determinant. The first column consists of coefficients current 1, second column current 2, third column current 3. So now how do we handle this, where we saw simply with the 2 by 2 that it was just this times this times this times this? Well, you can see from the next step it's a little more complicated. So what we have to do here is we have to rewrite the first 2 columns immediately to the right of the determinant. So we take column 1 and column 2, we rewrite it over here on the next column. And the reason for this is because we're going to do multiplying all of these, all of these, all of these, and taking the differences. So this just makes it easier to keep track of those values that we are adding to our product. So we identify the 3 downward diagonal groups of the 3 coefficients each, multiply the numbers in each diagonal, and add their products. So you can see then we have 1 times 4 times 6, there's the first one. 3 times 1 times -5, that's the second one. -2, 0, and 1 is the third one. So when we add those all together, we end up with a value of 9. Step 2 and 3, then we do the same thing, steps 2 and 3 for the 3 upward diagonaling groups of the 3 coefficients. So you can see now we have this group multiplied together, this group multiplied together and added, this group multiplied together and added. And when we take the products and the sums, we end up with 41. So now when we subtract the result from step 4 from the result from step 3 to get the value of the characteristic impedance, 9 minus 41 gives us minus 32. So that becomes our characteristic impedance for this 3 by 3. Next, form another determinant by substituting the constants on the right of the equations for the coefficients of I1 in the characteristic determinant. So we're going to go back to our first characteristic determinant. We're going to remove column 1, all of the I1 coefficients, and replace it with the voltage values 7, 8, and 9. Evaluate this determinant using the method described in the previous steps. Okay, so we're going to take the first 2 columns, we're going to move them out here to the side. So we do those 3 products and add them. Then we do these 3 products and add them, and then take the difference. And when we do that, we get a determinant of 100. So now solving for current 1 by dividing the determinant by the characteristic determinant, the negative result indicates the actual current in the direction opposite to the original assumption. So I take that minus 32, I divide it into 100, I get minus 3.125 amps. And so you would repeat this process then for current 2 and current 3. So it's not a difficult process, it's just time consuming and has multiple steps associated with it. So if we take a look at this example, given that the coefficients are in ohms and the constants are in voltage, we do the same thing. So the first thing we do is we take a look at it and determine, are all of our equations in standard form? And yes, they are. So we can now form our determinant, our first matrix here, load the values, and then set it up for doing the products and sum by taking the first 2 columns, annotating them here on the side, and then we do 1, 2, 3 products, add them together, and we end up with 2.35. Okay, so that's our characteristic determinant. Then we evaluate the determinant for I2. Okay, so we have these values. Again, we're going to go the opposite direction. Okay, so we have for I2 we have to replace again column 1 and column 2. You can see we've done that, and so now we have 0, 1.5, and minus 1 in there. Okay, so we do the same thing when we do our products, 1, 2, 3, and then do our additions, and we end up with minus 1.25. Okay, so you just have to do this. Take this example, work it out, pull out a piece of paper, pull out your calculator, and solve for this. So then the last step then for finding the current then is divide by the 2 determinants. Okay, so 2.35, which was the first step, minus 1.25, which was the second step, we get a value of minus 532 milliamps. Okay, so that way is the way that we solve for these values. In this case, they wanted us to solve for I2 from the following equations. Okay, so in the next step here, your text goes through and has you do a calculator example. What I suggest you do is follow through on this calculator example using your calculator. Again, everybody's calculator is a little different. Some may have functions that others do not. But pull out your manual. You know, for the Casio, you got a little manual that came with your calculator, and work through the relationship. Many of these calculators actually have matrix relationships that allow you to enter the matrix, and it will automatically do the determinants for you. All right, so we're going to go ahead and stop there. This is getting long already. The next section here, we're looking at determinants again using a two-loop equations, and we've got them here. It's just a rewrite of an example here, and we can walk through those. It's basically the same steps that we have already seen for solving for I1 and I2. So let's bail right here and go on in the next video.